All right, let's dive right in. We're going to talk about the most fundamental thing in existence, the blueprint for you, for me, for the entire universe. Yeah, we're talking about the atom.
But hang on, let's think about it this way. What if you had the actual instruction manual for reality? I mean, the ultimate guide to how everything works.
Well, here's the crazy part. It exists. It's real. And that manual, that fundamental rulebook for the universe, it all starts right here with the atom.
So let's crack open that manual, shall we? First up, the atom's inner secrets. We're going to unpack the fundamental parts list of, well, everything.
You know, for something as complex as the universe, the parts list is actually pretty simple. When it comes to chemistry, you've really only got three main players on the field. You've got your positive protons, they define what an atom is. Then you have neutral neutrons, they just add some mass, keep things stable. And then you've got the negative electrons. Now these are the real MVPs, the workhorses doing all the interesting stuff.
Seriously, just think of the number of protons as an atom's unique, non-negotiable ID card. If it has 6 protons, it's carbon. End of story. 8 protons, it's oxygen. Always. That number is the one thing that defines what element you're looking at. Okay, so protons give an atom its ID, right? But it's the electrons that give it its personality. They're the ones out there playing the game of chemistry, deciding how that atom is going to act and who it's going to hang out with.
So if electrons are the players, what are the rules of the game? Because it's not just random chaos out there. Oh no, all of their behavior, everything they do is driven by one simple, powerful desire. It all boils down to this: a quest for stability. See, atoms are kind of needy. They're totally obsessed with having a full outer shell of electrons. It's their version of a cozy, perfect home. And that one simple goal, that's the engine behind literally all of chemistry. All right, so to get that perfect, stable shell, atoms can't do it alone. They have to interact with each other. They have to bond. And to build everything you see around you, nature really only uses 2 main construction techniques.
It really comes down to 2 main strategies to get what they want. They can either give an electron away or just straight up take one. That's what we call ionic bonding. Or they can share electrons with another atom. That's covalent bonding. So it's basically a choice between being a thief or being a teammate.
And I gotta say, this analogy for ionic bonding is perfect. Imagine a puppy thief. One atom is way bigger and stronger, and it just rips an electron, the bone, right away from a smaller one. So now the thief has an extra negative charge, and the victim is left with a positive charge. And what do opposites do? They attract. They get stuck together. And that's really all an ionic bond is, scientifically speaking. It's just that super strong, almost magnetic force holding those 2 charged atoms, our thief and our victim, together after the great electron heist is complete.
Now, the other way to do it is way more cooperative. Covalent bonding is more like 2 puppies deciding to share. So instead of stealing, they each get a paw on both of the electron bones, holding onto them together. That way, they both feel like they have a full set.
And yup, that's a covalent bond. It's a real partnership. By sharing those electrons, both atoms get that stable, full outer shell they were desperate for. And this new partnership creates a single, stable unit that we call a molecule.
Okay, that's great. We've got theft and teamwork happening on a crazy small scale. But so what? Why should you care? Well, because these incredibly simple rules are the reason the world you and I live in exists. They create everything we can see and touch. This is where it gets really cool. Take something with ionic bonds, like table salt. Those bonds are so strong, they form these tough little crystals that take a ton of heat to melt. But then look at something covalent, like sugar. It melts way more easily. See? The type of bond literally dictates how the substance behaves in the real world. But wait, there's another layer to this, especially for those covalent compounds. The bonds inside one of those sugar molecules are super strong, but the attraction between one sugar molecule and the one next to it, much, much weaker. We call these intermolecular forces. You can basically think of them as a kind of weak molecular glue.
And just like real glue, this molecular glue comes in different strengths. There are a few different kinds, as you can see, but here's the only thing you really need to remember. Hydrogen bonds. They are the superglue of the molecular world, by far the strongest of these weak attractions. And that little fact, that brings us to something we all know, water. We all kind of know it's special, right? It's a bit of a weirdo molecule. But why? Well, the answer is all about that molecular glue. It's because of those hydrogen bonds. That molecular superglue is what gives water all of its incredible, almost magical properties. It's why it can pull other things apart and dissolve them so well. It's the reason water is, quite literally, the solvent of life. And this is where we bring it all home, from the world around us to right inside our own bodies. Because these exact same rules, this exact same chemistry, is what's powering you at this very second. You know how you always hear about electrolytes in sports drinks? Ever actually wonder what they are? Well, it's super simple. An electrolyte is just an ionic compound, like plain old salt, that breaks up into those little charged particles, those ions, when you dissolve it in water, like the water in your body. And those little ions, they're basically your body's entire electrical system. They are what carry the signals for your nerves to fire. They trigger your muscles to contract. They manage your fluid balance, your pH. I mean, the fact that you can even think these thoughts right now literally depends on some salt dissolved in water. So think about that. From the atoms that were cooked up in the heart of a dying star to the tiny bit of salt that lets a neuron fire in your brain, everything plays by the same simple, elegant rules. We have the blueprint. We understand how it works. So the only real question left is, what else can we build with it?